Hello everyone, welcome to this lecture of the course Digital Electronics and Circuits. In this particular lecture, we will be talking about few certain concepts with respect to digital IC families, and I will be discussing three major concepts in this lecture, right? So basically, I would be touching upon something called as levels of integration. Number one, what kind of levels of integration do we have, right? Basically, we will talk about small scale integration, which is nothing but SSI. Then we have something like medium scale integration, MSI, large scale integration, and very large scale integration. The next set of things which we will be talking about in this particular lecture is IC logic families. So what all kinds of IC logic families are there, right? Something called on the lines of we have something resistor transistor logic, diode transistor logic, we have ECL emitter coupled logic, we have something called as NMOS, PMOS, and CMOS logic family, right? And eventually we will talk about few characteristics, right, based upon which we will evaluate that which particular IC logic family is something which we should be using, right? And these characteristics are the characteristics which will define these logic families. These are nothing but major things like fan out, propagation delay, which is nothing like TP, propagation delay. And in addition to these two, we have something called as noise margin, which is nothing but NM, and total dissipated power, which we call as TDP, total dissipated power. So this particular lecture, we will be talking about levels of integration, what kind of IC logic families do we have, what are the different characteristics of these circuits, correct? To begin with, right, if we talk about our level of integration, I spoke about SSI, which is nothing but small scale integration. When we talk about level of integration, we simply say that if we have a circuit, let's assume we have a two input AND gate, right? We will be talking about AND gate in detail, where we say output C is equal to A and P, right? So basically, this particular AND gate would be made up of a set of internal transistors, right? Transistors, or depending upon what kind of a logic we have, what kind of a logic family we use. We the basic constituents of this AND gate would vary depending upon the kind of logic we have. And basically, when we say small scale integration, it means how many transistors does a circuit have. Usually in small scale integration, we have less than 10 transistors, right? Or basically, if we say transistors, or we can simply say gates, less than 10 gates. Then we have something called as a medium scale integration, MSI, where we have something called as, let's assume something like, okay, we have something like gates in the range of say 10 to 100, right? And we will have some elements. For example, let's assume we have some flip-flops. We will be talking about what is a flip-flop, how do we model a flip-flop, or what kind of a, how does the flip-flop operation happens, right? Or in case we have something called as adders, if we have to add two numbers, say C is equal to A plus B, in order to realize this on a hardware, all the things, all this internal circuit would be made up of universal gates, NOR gate and NAND gate. But those particular gates would further be, we will have a set of combination of those gates, or that particular circuit, which will have something in the range of 100, 10 to 100 gates, or 10 to 100 transistors, which will form a medium scale integration. Then we have something called as LSI, large scale integration, which is usually in the range of say 100 to 10K sort of a thing. One particular example of large scale integration is memory elements, whatever we spoke about in our lecture one, right? And we will be looking at it like how these memory elements are requiring a gates which is in excess of 100 up to 10K. So they will form a, they will fit into a scale of large scale integration. And eventually we have something called VLSI, which is nothing but very large scale integration, where we have a transistor in excess of 10K going up to all the way in millions and billions, right? So basically you can say that all the large memory chips, all your memory chips, basically all the computer circuits, all the chips on which your computer is operational, they form a part of VLSI, correct? So basically I can simply say large chips, different graphics cards or your onboard graphics, your basically processing units, CPUs, they form under a category of VLSI, correct? And I'm assuming that whenever we talk through the small scale integration, medium scale integration, LSI and VLSI, right? How so basically one interesting fact to notice over here is how the world moved from small scale integration to medium scale integration to large scale integration and eventually to VLSI. So I'm not sure, but I think most of you would have heard about the term called Moore's law, right? So basically Moore's law says that after every 18 months, the number of transistors will double on a chip. This is what Moore's law states basically. So basically, given a same area, you would be able to pack, if this is a area, say A and B, right? We are able to pack, say, 10 transistors over here. After 18 months, in this particular area of A and B, you will be able to pack 20 transistors. This is because your gate length, right? Gate length decreases by a factor of root 2. So your let's assume that over here the transistor gate length was GL2 and the transistor gate length was GL1. So basically GL1 is root 2 times GL2, which simply means that you could pack double the transistors in the same area. This particular shrinking, this particular concept of Moore's law over a period of time has resulted in shrinking of gate lengths, and eventually we moved from SSI to MSI to LSI to VLSI, right? And as and when more and more transistors started getting packed into a chip, the number of transistors increased. Multiple other things like power, performance came into picture, which we will be touching upon basically in this course, but these are out of the context of this course, like how basically how is power calculated for a given set of circuits, or what are the performance constraints, right? We will be talking about basically about like what kind of IC characteristics are there, but just to give you a perspective of like how the evolution happened, how a particular AND gate or a OR gate or a NAND gate consist of SSI, small scale integration, how from here we move to concept of flip flops or adder circuits or multiplier circuits to small memory elements, right, to basically large chips. So this is nothing but different levels of integration which I wanted to talk about. And then we have something called as different IC characteristics. Okay, so basically we know that, okay, fine, we have set of transistors, we have set of gates, and I'm sure you would have heard about different logical families, being a resistor transistor logic, diode transistor logic, ECL emitter coupled logic, TTL transistor logic, and then N-type MOS, P-type metal oxide semiconductor, and then something called as CMOS, which is nothing but combination of NMOS and PMOS, right? So each of these logical families have their own set of constituent elements or transistors, as we would say. And how do we choose like which particular family of IC logic we need to use, right? So for this, for usage, we need to have some sort of a evaluation criteria, right? When we are looking for an AND gate, how do we make AND gate? Which IC logic family we should use to make an AND gate? So basically, choosing which family to use, we need to have some sort of evaluation criteria as to how uh, this particular set of logic families behave for a same set of operation, right? So the evaluation criteria, we will have something called as IC characteristics. That what all are the different characteristics of an IC. Based upon these characteristics, we will these characteristics would help us decide which particular kind of IC logic family we should be using. And these characteristics are nothing but fan outs, the four things I mentioned in the in the previous foil: fan out, propagation delay, total dissipated power, and noise margin. So basically, if we have to look at all these logic families, right? First of all, what we should do is we should look at all these IC characteristics and try to understand what IC characteristics are. What is the meaning of a fan out? What does a PD means? Power dissipation, right? And TDP, propagation delay, and noise margin. So basically, right, let's start with fan out. So what does a fan out means? Fan out is nothing but, let's assume we have a circuit. Say we have an, let's assume this is a NAND gate, and this particular NAND gate feeds into few others NAND gate in the circuit. Let's assume we have a circuit like this. Like, so let's assume basically there's a IOH coming out of here, and then basically this has IIH level, this has IIH level, this has IIH level. So basically fan out means how many gates an output can drive without any loss of data. Okay, higher the fan out, better the circuit is. If my this particular NAND gate, let's assume if I say this particular NAND gate could support up to 5 outputs, right? So basically I could basically tap this output over here using 5 other gates. 5 other gates could tap its output. Whereas let's assume there's some technology through which this NAND gate is formed, and the technology says okay, only 3 gates could be driven. So basically what would that mean? Only 3 gate can tap into this IOH logic. So basically if at all the circuit requirement is such that 2 more NAND gates need to be driven out of this particular IOH, right? What we need to have is like we need to have set of buffer logic in place, correct? So fan out is something, one of the important IC characteristics where we say that okay, how many gates can an output drive without any loss of data? Higher the fan out, better is the circuit, correct? Once we have covered fan out, we should look at something called as propagation delay, correct? For this particular example, let's assume we have a NOT gate. Say this is input, this is output, I and O. Let's assume a time graph where we say our value I was something behaving something like this. It ramped up to a value 1 and it went to 0, correct? So now ideally speaking, what should happen if a circuit value is 1 0 over here? It will become 1. This is a operation of NOT gate. And if a value is 1, the output would be 0, right? But ideally in a circuit, what would happen is the value at the output will not change from to 1. When the input changes to 0, the output value should ideally change to 1 as soon as input changes to 0. But in a real circuit we have a concept of propagation delays, whereas there will be like whenever there will be some delays which this AND gate will intrinsically take depending upon the what kind of a logic family it belongs to, before ensuring that the output gets a value 1, right? So let's assume if the input was something like it went from 0 to 1, right? This is a 0 level, this is a 1 level. And so basically we would say like the output was 1, it went to 0 over here, and then it ramped up to 1, correct? Basically if you see over here, what is happening is the at the we usually take this whenever a propagation delay is calculated, we usually take 50% of the ramp up time and 50% of the time over here. We say that there is a delay, whereas we were changing a value from 0 to 1 at the input, that value is reflected at output with this delay. So basically we call it like propagation delay, correct? High to low, correct? My output changed from high to low. Similarly, at this end over here at 50%, right? Similarly, at 50% here, there is a delay over here as well, and we will call this delay something called as propagation delay low to high, correct? So now, what kind of IC family would be preferring in case of propagation delay? Ideally, we want our input, and ideally, what we want ideally we want any change in input to be reflected on output instantaneously. Basically, instantly, it should reflect on the output. Basically, what would this would mean? Basically, we want to make sure this trends to zero. Basically, that would mean like lower the propagation delay, better circuit, correct? So basically, now assume that we have understood the concept of noise, basically fan out, how many gates an output can drive without any loss of data or information, and a propagation delay. So these are the two of the evaluation criteria for choosing an IC logic design family. Moving ahead, right, we have something called as a noise margin. As the term suggests, noise margin, correct? Let's assume we have a circuit, something like this. Let's assume this is our driver, this is our receiver, right? Now, what we say over here is, in terms of noise margin is, let's assume the characteristics of this particular family was something like this. That see, this is a voltage level, okay? So when we say that voltage level, say this is a value 0. Let's assume this is a maximum value, say VDD, correct? Concept of noise margin says that if a particular value, let's assume this is like VOH, this is like V output lower. So basically, concept of noise margin is something like this. So basically, in this circuit design, what would happen is any voltage level which is less than VOL will assume a value of 0. Any voltage level which is above VOH will assume a level 1. Right? So basically, we would say the noise margin of this circuit is something like this is my output range. If my output is going as 1, it should be a value in the range of this to this, and basically VOH to VDD. And if my output value is going as 0, it should be in the range of VOL and VOH. Now let's assume the particular characteristics for this particular receiver over here is such that we have something called as just to create an example, let's assume it has a higher value over here, and it has a higher, basically it has a higher range on both the sides. Let's assume it's a V input high, this is V input low, this is 0, and this is VDD. Now basically, if we plot a graph over here and then we plot a graph over here, right? So this particular difference over here would be called as noise margin, right? So basically, our circuit has this particular set of noise margins, and smaller the noise margins, the smaller this value is. And this means that circuit is more sensitive to noise. Larger noise margin would mean that the circuit has more tolerance for noise, correct? So a better circuit is the one which would have like more tolerance, correct? So basically, if basically what this means is, right, if I am sending an output logic VOL and it receives as VIL, and if there is some noise margin is something like this thing, let's assume this noise, let's put some realistic numbers to it. Let's assume this is 0, this is 5, this is 3, this is 2. Let's assume this is 5, this is 2.6, this is 2.4, this is 0. What the concept of noise margin says is, if I'm setting a value of 0, and let's assume due to some fault in the circuit or due to some other dependency, this value reaches at 2.3 over here. let's assume we sent a signal at level 2. There was some noise margin. Let's assume there was some noise. Let's assume this is a white noise of zero point 0.3 and my output voltage is 2.3. Basically, if this, and I say that lower upper limit is VIL is 2.4, which means 2.3 is less than 2.4. So if I send a 0, it will be interpreted as a 0 only. Whereas what would happen is, in case we don't have this noise margin, or let's assume this noise margin was less, this was zero point 0.2, and we send this and the signal picks up a noise of zero point 0.3 voltage levels, right? We would say that okay, our the signal value over here is 2.3, right? Whereas my upper limit of voltage was 2.2. Now it will fall into this unknown region, right? Basically we cannot determine it, so basically this is called something like indeterminate region. So once we fall into this particular region, right, the value is non-deterministic, it could be anyone. So therefore, similarly for the upper one as well, right, if at all there was some degradation in the circuit, we sent a value of 3 which was triggered as a logic level 1. Let's assume that the value degraded by 1 voltage level. So 3 sent out of output receives at reaches as 2 in the input receiver, right? What would this mean? A signal which was having a value 1 at the sender or at the driver will reach as 2 volt at the receiver, and 2 volt over here would fall in the value of a 0. So a signal with a value of 1 is interpreted as a value 0 in the receiver side. So if there's a lot of noise in the circuit, what was happening is, and the noise margin is pretty less, what would happen is the logic value may be flipped from 1 to 0, right? So that's why this particular characteristic is very important. More tolerance, better is the circuit. Less tolerance, the circuit is not that preferred, correct? Now one last concept of total dissipated power, which we simply say as TDP, total dissipated power. Power is nothing but we have already read, it's like V into I. So voltage across a circuit multiplied by the current which is going through the circuit will give us the power. And in the general rule of thumb is usually more, if you need a more power is dissipated by the circuit. If a circuit is operated by a battery, the battery would need a recharging every now and then, right? Again and again, as compared to one the circuit which VI is lesser, right? So more the VI, more power consumption. If it is like so basically if the power consumption is more, right, either we need to have battery recharge available, right? If we have it available, we have to do it again and again. And or basically if we have it keep always, it's always on power, right? It's always on, power consumed will be more. Similarly, if lesser the VI, total dissipated power would be less. And if power is less, what would happen is a longer duration for battery. Correct? So just to recap, we spoke about 4 characteristics. The first one being fan out. So larger the better. Then we talk about something called as propagation delay. Propagation. So basically higher the better. Propagation delay has to be lower, and lower the better. Then we have noise margin, higher the better. Then we have total dissipated power, lower the better. Correct? These are the characteristics based upon which we will choose which IC logic family should be used for our circuit, for designing our circuits, designing our digital circuits. Correct? I hope this is clear by now. So basically we spoke about important concepts over here. We started with something called as a level of integration. We discussed like how many gates will comprise of SSI, similarly MSI, LSI and VLSI. Then we spoke about different characteristics based upon which we would decide which of these IC logic families to use to form our circuits, right? And at the end basically we looked at all these things. We looked in detail into fan out, propagation delay, noise margin, TDP, and eventually one thing which is left and which I want to touch briefly, not in details, but basically what kind of IC logic families are there. We have RTL logic, which is nothing but resistor transistor logic, correct? Correct. And then we have something called as a DTL, which is nothing but diode transistor logic. We have something like TTL, transistor transistor logic. We have ECL, emitter coupled logic. Then we have something like metal oxide semiconductor, NMOS, N-type, PMOS, and then we have a combination of CMOS, a combination of NMOS and PMOS, which will form CMOS. Now, basically, resistor transistor logic will have a resistors plus transistor. This will have diode plus transistor, correct? This will be nothing. TTL is nothing but transistor plus transistor. Emitter coupled logic is nothing but it used like bipolar junction transistors, BJTs. And then we have MOS logic. This is like N-type, P-type, and this is like combination of both N-type plus P-type, right? So as an example, right, if we start looking into various characteristics of these logic, I would want to tell you about basically if we compare three particular logics, right? Basically, if I just pick up TTL, ECL, and CMOS, right? And if we have to evaluate like how this TTL, ECL, and CMOS compare against each other on set of different parameters which we spoke about, right? Fan out, noise margin, propagation delay, and TDP. So this would look something like this. Let's assume we have one of our characteristics, say fan out is something which we talked about in the beginning. Then we talked about something like propagation delay. We spoke about noise margin, and then at all we spoke about TDP, total dissipated power. Now basically these are different characteristics. If we try to compare, so basically this is something like a known fact which I am telling you. If we compare TTL versus ECL and CMOS, what we would see over here is, right, this particular thing TTL will have a fan out in the range of 1 to 10, ECL will have close to 20 to 30, and CMOS will have greater than 50. So CMOS win hands down in fan out. Basically, fan out is pretty large for CMOS circuits. Now, if we talk about total dissipated power, and whenever we, whenever we talk about TDP over here, right? If we look at power for TTL would be in the and okay, whenever you talk about power, right, we have to put some dimension to it. Let's assume we are talking about power in multivolts. This power dissipated for a TTL circuit would be in the range of say 10 watt, 10 milliwatt. And similarly for ECL, right, this would be something in the range of 50. But for CMOS, this would be less than 1. So you can say like it would be, or I would simply say this will be like less than 1 by 100 also. Correct. So CMOS has a lower power dissipation. This we will talk about why it has a lower power dissipation. That is because how both PMOS and CMOS are connected to each other, the different sources and drains. We will talk about it. But if we have to compare the characteristics, right, CMOS wins hands down in fan out and TDP. Now, if we look at noise margin is very high for CMOS circuit. It's moderate for TTL and very low for ECL. Again, CMOS circuits wins hand down in noise margin. And in term of propagation delay, right? Whenever we talk about propagation delay, we have to have some unit associated with it. Let's assume nanosecond, right? In terms of nanosecond, propagation delay varies quite like vastly. It is from like 1 to 30 for TTL. For ECL circuits, propagation delay is usually very less. It's from 1 to let's assume 6 or 7. And then for CMOS, the range is pretty wide. Correct. So this is how three different categories like TTL, ECL, and CMOS compare against each other in terms of these different IC families, right? And why did I compare TT and these families only, right? Because these families are very very famous. Basically, all the NAND gates which are like of the series of what we say 74, 7410, 7404, all these universal gates and all the gates in this particular series, they are formed using TTL logic. And similarly, for ECL, emitter coupled logic families, we have high BJTs, right? And the advantage, one of the advantage being the low propagation delay for ECL families. And basically, this is nothing but your set of BJTs. And CMOS is something which is like these are like, as of today, these are forming backbone of VLSI industry because everything is formed using CMOS logic. So this was a lecture where I wanted to touch upon a few basics. This will not directly impact or help you understand our digital electronics course, or this is not something which is must know for learning what is a resistor circuit look like, what does a counter looks like. But basically, before we begin a digital electronics course or we talk about digital circuits, we need to know about what kind of our digital IC families are there, right? What, how do we compare digital different digital IC families, and what are all those parameters based upon which we would compare these families before choosing which family to work with, right? And as a matter of fact, as a fact, right, what you understand is like, fine, we have like different set of characteristics. CMOS is something which forms a backbone of VLSI industry, and there is a reason why that is the case, and that is because it has different characteristics of all the different families. It stands out as compared to other families of logic design. And we just spoke about one basic other concept as well, what is SSI, MSI, LSI and VLSI, and how what Moore's law is, if at all you didn't know about it. Correct. Thank you for attending this lecture. See you in the next lecture.